Hello everyone. Welcome to the 10th problem solving session for the course Introduction to Lasers. And I'm Haskaja. I'm going to discuss about some problem today. So I will just wait for a few minutes for people to join, and then I will start. Okay, so hello everyone. I'm Bhaskarja and welcome to the problem solving session of the course Introduction to Lasers. So in the course you are being taught about the pulse laser and also the pulse laser and the methods of generating the pulse laser like Q switching, mode logging. So I'll discuss some problem about that. But before going into the problem, I will just write down one formula so that we can understand the problem better. Okay, so we're going to use this formula. Now I will just write down the question. So the first example here, the question is, what is the maximum what is the maximum Q switched power output from a UV laser with a chromium concentration of 1.6 into 10 to the power 25 chromium ions per cubic meter. So the question is, what is the maximum Q switched power output from a UV laser with a chromium concentration of 1.6 into 10 to the power 25 chromium ions per cubic meter. Now the given information in the problem is, assume a UV laser rod of 0.1 meter long and cavity length of 0.4 meter, and the mirrors for the cavity coated with the material of reflectivity of 90%, and also it is given that the index of UV is 1.75. and the diameter of the laser rod is here. So now another question is, determine the Q switched power output from the laser if it is pumped to a factor of 5 times the threshold inversion density. Okay, so the problem is, statement of the problem is very big to be precise, and then so the first question is, what is the maximum Q switched power output from a UV laser with a chromium concentration of 1.6 into 10 to the 25 chromium ions per cubic meter. Then there are some information about the laser, that is the UV rod is of 0.1 meter long, cavity length is of 0.4 meter, mirrors are coated with 90% reflectivity, and index of the UV is 1.75, and the diameter of the laser rod is 2 mm. Then the second question is determine the Q switched power output from the laser if it is pumped to a factor of 5 times the threshold inversion. So for the first thing is the what is the maximum Q switched power. For that I will use this formula. So here I will just write the formula again. P max H mu U T C. So N T H ln N T H N naught minus N T H minus N naught. Okay. So now N naught by N T H is given 5. So this is basically this inverse this statement, that is it is pumped to a factor of 5 times the threshold inversion gas. Okay, and UV laser has a wavelength of 694.3 mm. That will give H mu equal to 2.86 into 10 to the minus 19 joule. Now the parameter Tc, which is basically the cavity decay time. Tc. So this is not going to be a straightforward formula, rather than the Tc will be calculated with this formula NLL. Eta LL, eta L multiplied by L, and eta C multiplied by D minus L by CLL. So now I'll write that eta L. So eta is the refractive index of the ruby rod, that is 1.75 multiplied by 0.1 plus eta C, which is the air, then D minus L. So that will be cavity length is 0.4, so it will be 0.4 minus 0.1. Then C is 3 into 10 to the power 8 meter per second, and then LF is 0.1. So basically the LF is the length of the ruby rod, so after calculating this we have 1.58 into 10 to the power minus 8 second, 1.5 into 10 to the power minus 8 second, which is 15.8. So this is 15.8 nanosecond. So this is the value of TC. So now we'll get back to the calculation of Pmax. So Pmax was h nu by 2Tc. So h nu was 2.86 into 10 to the minus 19 joule by 2 into Tc. Tc is 1.58 into 10 to the minus 8. Now NTH ln 1 by 5. So basically this is from the m0 by mt is equal to 5. So this is 1 by 5 because here we have the inverse mth by m0, and then minus mth minus 5 mth. So basically we have m0 here, so we replace that with the 5 mth so that the ratio is 5. Now 9.05 into 21 minus 12 joule per second, and here it is minus 1.61 mth plus 4 mth, which is given as, which will be 2.16 into 10 to the power minus 11 mth joule per second. So now we need the value of mth. So the concentration of chromium is 1.58 into 10 to the 25 per meter cube. Now the mth will be 1.58 into 10 to the 25 by 2 multiplied by V. So here why we are dividing the concentration by 2, because in order to have a population immersion at least 1.58 in the half of the concentration should be pumped to the upper laser level. So that's why we are dividing it by 2, and then this V. So V is the total volume occupied by the laser mode within the rope. So the V will be pi 0.001 0.1. So this 0.001 is basically the radius. So the diameter of the laser rod is 2 mm, so the radius is 1 mm, and that's why I have written this 0.001 mm radius, and then the 0.1 is the length of the rod. So that will makes the volume is 3.14 into 10 to the minus 7 meters square. Hence mth will be 1.58 into 10 to the 25 by 2 into 3.14 into 10 to the minus 7, which will be 2.48 into 10 to the power 18. Now we can calculate the Pmax. that is 2.96 into 10 to the power minus 11 into 2.48 into 10 to the power 18 joule per second. So this gives 5.36 into 10 to the power 7 watt, which is closely 50 megawatt. So this is the power output of the laser pulse, that is 50 megawatt. So basically in this problem we have two questions that so basically we have a question to determine the power from the UV laser with the chromium density concentration of 1.6 in 10 to the 25 chromium ions per cubic meter, and we use this formula from the Q switching and calculated that the Pmax will be 50 megawatt. So this is a substantial power output of a laser pulse. Okay. Now I will discuss about the topics, that is methods of producing Q switching within a laser cavity. So first one is the rotating mirror. So basically in Q switching what happens is that we change the Q of the cavity. So basically in Q switching we start with a high cavity loss and then pump the population to upper laser level until the gain approaches the loss, and then switch cavity on net loss. The loss is significantly reduced and the laser pulse start to initiate, and then we have a Q switched laser output. So in order to control that uh, control the loss of the cavity, we have different methods. So the first one is the rotating mirror method. So this was the first method used for Q switching laser. This is a mirror. This is the amplifier. And then here we have the rotating mirror. So it is a hexagonal shaped mirror on a rotating shaft, and aligning the facets of the mirror with the laser cavity such that for every sixth of a rotation of the shaft, a mirror would be aligned with the laser cavity as shown in this figure. So basically this mirror is continuously rotating, and every sixth of the rotation of the shaft, the mirror will be faced like this. So that will make this as a cavity. So this mirror will serve as a real mirror of the laser cavity, and an output mirror would be located at the other end of the cavity. So now suppose for ruby laser, the upper level lifetime is of 3 upper level lifetime is 3 milliseconds. So then this hexagonal mirror so hexagonal mirror will turn 1/6 in 0.003 second, or a full turn in 0.018 second. So basically the rotation speed of this mirror is controlled by the is determined by the upper level lifetime of the gain medium. So basically this corresponds to 3.333 rpm of the shaft. So this is a high rotation speed. So now basically what happens is that the mirror will face to the amplifier at some point, and then it will rotate for some amount of time, and then again it will make its reflecting face towards the amplifier. So basically at that point of time it will act as a real mirror. So this is the uh, time limit of the rotation for the mirror. Now the problem with this method is that the rotation should be uniform and the mirror cannot be very big, as if it is very big then it will cause some kind of vibration problem in the cavity, which is not desirable in the laser, because we need to stabilize the laser as much as possible. And another problem is that the mirror should be the alignment of the mirror should be ideal with the shaft, and that is also little bit problematic, because if there is a problem with the surface of the mirror, then this the rotation, even the rotation is perfect or we can control the rotation, our main point of having a Q switched laser will not be possible. Now the second thing is the electro-optic shutter. So electro-optic shutter is very fast optical device for switching from a high loss to low loss. Fast optical device to switch from a high loss to low loss cavity. So the property of the electro-optic shutter is basically an electro-optic crystal that becomes birefringent when an electric field is applied across the crystal. So basically there is a crystal and this crystal becomes birefringent when electric field is applied. So basically this what this shutter do is that the crystal do it basically rotates the polarization axis of the beam. So the laser must have a polarizing element within the cavity. So then the point is that there is a polarizing element inside the cavity that force that laser to works on for a certain polarization. So that particular element will allow the beam to enter the cavity when it is has a certain polarization, and this particular electro-optic shutter will change the polarization with a certain time constant. So basically at some point the beam will enter the cavity, and when the electro-optic shutter is switch on, and it will not allow the it will change the polarization axis, and then the polarizing element that is inside the cavity will not allow the beam to enter the cavity. So basically when the voltage is so so basically when the voltage is on, so the figure is something like this, which is also same as the previous one. So you have to measure here the amplifier, and this is the shutter. So now when the voltage is on for this electro-optic shutter, what happens inside a cavity is the polarization rotated 45 degree for each pass through shutter. So basically the polarization rotated 45 degrees, so the beam which is coming from this side, so it will pass the shutter and have a 45-degree polarization difference. Then from after reflecting from this mirror, it will again come here, and then it will have a 45-degree polarization difference. So that will make that the returning beam to the amplifier is rotated 90 degree. 90 degrees. So as we know that the polarizing element, so suppose this is a polarizer and it has a plane of polarization in this, then if the polarization axis is changed like this, so basically we have a 90-degree shift in the polarization axis, then this beam will not pass the polarizer. And then so basically after passing 2 times from through the electro-optic shutter, it will not go to the amplifier, and then it will create a high loss cavity. So the polarizing element will reflect back the beam and it will not reach the amplifier. And when the voltage is off, so beam passes through the shutter will be undisturbed so this will make a low loss cavity. Okay, so this is how electro-optic shutter is used to change the Q loss of the cavity. So it will generate a high loss cavity when on, and it will create a low loss cavity when off. Now there are two types of electro-optic shutter that can be used for Q switching. One is focal cell and another is card cell. So for focal cell, here they use the focal effect. So focal effect is produced when an electric field is applied to certain kinds of bireframe crystal to alter the indices of diffraction of the crystals. So here for focal cell the material is used that is known as KD*P. The full form is I'll just write this in a page. So this is KD*P, which is the full form is potassium dihydrogen phosphate, and another material is CD*A, that is the cesium dihydrogen arsenate. So these two materials are used basically for the reason is they require least voltage to produce the desired effect. So now the focal says that, so this when we apply a voltage to the focal cell, it provides a rotation of the polarization of the beam that is proportional to the thickness of the cell and magnitude of the field. So basically this is actually the rotation of the polarization is dependent on the thickness and the magnitude of the electric field. So the field is basically applied in the direction of optic axis of the crystal and in the direction of the optical beam. So this is the focal property of the focal cell, and this is the two material that is used for focal cell. So let's say this is the focal cell and it has an optic axis like this, then the electric field will apply in this direction, and the change in the polarization will be proportional to the magnitude of the applied electric field. Now next is the thing is card cell. So this is not a crystal, this is just a isotropic liquid, isotropic liquid. So this isotropic when electric field is applied normally to this isotropic liquid, it will act as a doubly refracting. By aligning, it will become doubly refracting. So doubly refracting means that it will act as a birefringent material. So here the birefringent effect is proportional to the square of the applied voltage, and the material that is used here is mainly liquid nitrobenzene. So why liquid nitrobenzene? Because the reason is same, that it creates the desired effect. Creates the desired effect at low voltage. Now there is another thing that is known as the acousto-optic shutter, is also used for precision. So acousto-optic shutter typically uses a quartz crystal. So the configuration is same as the previous one, but we have a mirror here. So this is a quartz crystal with a RF transducer. So basically the transducer is controlling the orientation of the quartz crystal. So the quartz crystal has a piezoelectric transducer attached to the crystal that propagates strong acoustic waves within the crystal when RF signal is applied to the transducer. So when this field is applied during the time the amplifier is being pumped and the laser beam is deflected out of the laser cavity by an effective diffraction grating that is established by the acoustic waves propagating by the RF signal. So when there is the RF signal, there is a diffraction getting created here. So when RF frequency is on, RF means the radio frequency is on, the beam is deflected out of the cavity, yielding high loss and RF of Q beam transits the cavity with low loss. Then there is another thing that can be used for Q switching, that is saturable absorber. So this is a passive Q switching element. Till now all the things we have are directly controlled by the some external thing, that is here we have a radio frequency. In these two cases we have a electric field, so basically electro-optic shutter. Then we have a mechanical lead driven mirror, so we have all these things. But saturable absorber is a passive Q switching element. So this saturable absorber is also used for mode locking, but here I am talking about the Q switching. So the absorber would normally appear as a high loss element, highly absorbing at the laser frequency. So it is basically placed at the same place like the previous ones. This is a mirror, this is another mirror, this is the amplifier, and then here we have the saturable absorber. So by the name we have that saturable absorber. So basically this is the element that will automatically absorb the light, and that is something saturates at some point. So when the absorber would normally appear as a high loss element, basically highly absorbing. So the saturable absorber is initially a high loss element. or highly absorbing element, so the beam is mostly absorbed by the material at the laser frequency. As the laser crystal is formed, the spontaneous emission at the laser frequency becomes more intense as the higher upper laser level population continue to increase during the pumping cycle. So now at some point this absorber will be saturated and it will not absorb anything, and it will become a transparent type of thing, and then it will at that point the beam will pass through the saturable absorber, which is in scientific term it is known as bleach through, so it cannot absorb any further light, and it will act as a transparent material and thereby creating low loss in the absorber. So now this will create a low loss cavity, and at that time the beam will begin to traverse back and forth and begin to build up within the cavity. A good saturable absorber can be determined by ensuring that the laser intensity at the time it arrives at the absorber the laser intensity at that time it arrives at the absorber multiplied by the absorption cross section of the absorber. This quantity should be greater than the intensity of the laser as it arrives at the gain medium multiplied with the stimulated emission cross section of the gain medium. So this is the criteria for a good saturable absorber, that is the laser intensity at the time it arrives at the absorber. So intensity at the absorber multiplied with the absorption cross section of the absorber is greater than the intensity of the laser arrives at the gain medium multiplied by the stimulated emission cross section of the gain medium. So if we write down the mechanism, when the amplifier is pumped with sufficient energy, the emission from amplifier saturates the absorber, causing it to change from high loss to low loss. Okay. So high loss to low loss, and then a pulse of light to pass through the absorber. So mainly liquid dye is used for this kind of thing. The name is DODCI. So this is how the Q switching works for with the defined methods. Now I will go to some problem of this Q switching and mode locking. So I'll first write the problem. So in this designing an unstable resonator for a 248 nanometer krypton fluoride excimer laser, the separation so now the problem is in designing an unstable resonator for a 240 nanometer KRF excimer laser. For practical consideration, it is desirable to have a relatively long gain medium such that the separation between mirror is 0.5 meter. Now for a magnification factor of 5, what would be the degree of curvature of both the output mirror and the rear mirror? What would be the degree of curvature curvature of both output mirror and the rear mirror. So the laser cavity ought to be designed for minimum diffraction losses. What will be the diameter of the output mirror? So now there are two questions. One is what would be the ratio of curvature of both the output mirror and rear mirror? Another question is if the laser cavity were to be designed for minimum diffraction losses, what would be the meter of the output mirror? So now the given thing is the separation between mirrors is 0.5 meter. So and the magnification are R and RO. So capital R small r is the radius of curvature for the rear mirror, and the RO is the radius of curvature for the output mirror. It is given as 5. RR minus RO is equal to 2D. 5 R0 minus R0 equal to 2D. R0 equal to 2D by 4. D is 2D by 2, 0.25. T is 1. So RR is 1.25 meter. Now we'll calculate the Fresnel number, that is denoted as n minus 1 by 2n square s square by lambda d. So this Fresnel number is calculated for to get the loss. So now we have 5 minus 1. Now as we have mentioned in the problem that it will have a minimum diffraction loss. So for minimum diffraction loss, using this formula we need to have this n equal to 0.5, 1.5, 2.5, etc. So now here we will calculate for 0.5. So this is a basically you can have this as a note that in order to have the minimum diffraction loss we need to calculate the NEQ, and this should be equal to 0.5, 1.5 or 2.5. So now here we will get this with 0.5. Then we have n minus 1 by 2m square then it is 5 minus 1 2.2 into 5 square a square lambda equal to 0.5. And if we simplify we will have a square equal to 0.5 lambda d t by 4. So a square equal to 0.5 into lambda d into 50 by 4, then 0.5 into 248 into 10 to the minus 9 into 0.5 50 by 4. Then we will have a equal to 8.8 into 10 to the minus 4.88. Yeah. So the diameter will be 1.76 mm. Okay. Now we'll have a analytical problem. So for a unstable resonator from this equation and using the usual notation obtain this. So now as we have mentioned in previous session, then G1 is 1 minus d by r1 and G2 equal to 1 minus d by r2. So now r1 equal to r0 and r2 equal to minus r0 because r0 has a sorry. So r0 has a negative the output mirror has a negative curvature, so we can put minus r0. Now that will make that G1 equal to 1 minus d by r and G2 equal to 1 plus d by r0. Now if this is the case, then we can use that here and we will have, okay, so I will not write in the problem, rather I will write r r0 to d, this will become rr plus r0 equal to 2d. So basically then this g1 will become 1 minus rr plus r0 by 2 rr, and g2 become 1 plus rr plus r0 by r0. So again you can write this as 1 minus half plus r0 by 2 rr. So g1 is 1 minus half plus r0 by 2 rr. This half of 1 plus r0 by rr, and then similarly we can obtain g2 equal to 1 plus rr plus r0 by 2 r0, which is the half of 3 plus rr plus r. Then we will multiply g1 and g2, and we will have 1 by 4 3 plus 3 r0 rr plus rr by r0 plus r0 r by r0. This will be equal 1 by 4 plus 3 r0 by rr plus rr by r0. And on the other hand, g1 plus g2 is half 1 plus r0 by rr plus 3 plus rr by r0, which gives us half 4 plus r0 by r plus rr by r. So basically we have g1 plus g2 equal to 2g and g. So this derivation is not necessary, but there might be MCQ question which will ask what is the relation between g1 and g2 for unstable resonator. So this is the relation, and here is the derivation. So in this example, the problem is a point 1 meter long ND laser rod is installed in a 0.4 meter long laser cavity of a Q switched laser. Determine the approximate value for TS and Okay, so the problem is that a 0.1 meter long ND-YAG laser rod is installed in 0.4 meter long laser cavity of a Q-switch laser. So determine the approximate value of TS. So L is 0.1 meter ND-YAG, D is 0.4, and some information about the ND-YAG laser. So eta L is the 1.82 and lifetime of the upper laser level in ND-YAG is 230 microsecond. GTH NA is 12, where NA is the effective gain length. So now M is equal to 12 by GTH L, that is 12 by 10 meter inverse 0.1 M, that will be approximately 12. So now the minimum gain duration TS for the beam to reach ISAT is TS and eta C D minus L plus eta L divided by C. Now putting all the values, 12 multiplied by 1 into 0.4 minus 0.1 plus 1.82, that is the repetitive of the ND-YAG, multiplied by 0.1, that's 25 by 8. Given, so after calculating these values, we will have 1.9 into 10 to the power minus 8 second, which is 90 nanoseconds. So a 0.1 meter long UV laser rod has the mirrors coated on the ends of the rod. The output mirror has a reflectivity of 90%. And reflectivity of the rear mirror is 99.9%. If there is no excited state absorption, that is alpha equal to 0 in the laser, what would be the fractional loss per pass in the laser cavity, and what would be the decay time of the cavity. So here we have a laser 0.1 meter long UV laser rod. The reflectivity of the output mirror is 90% and the reflectivity of the rear mirror is 99.9%. So if there is no excited state absorption, that is the excited state absorption of coefficient is 0 in the laser, what would be the fractional loss per pass in the laser cavity and what would be the decay time of the cavity. So first we will calculate LF. LF is alpha L minus ln R1 R2 half. Now here alpha is given 0, so LF equal to minus ln R1 R2 to the power half is minus half ln point 999 and 90 0.0. So this gives 0.053, and now TC equal to NDCLF. So here the TC is very simple, that is NDCLF, but as this is because we have in the problem that the 0.1 meter long UV laser rod has the mirrors coated on the ends of the rod. So basically the laser rod is ending here, and then at that point in the cavity we have the mirrors. There is no space between the mirror and the laser rod, but if we don't have that, then there will be this kind of formula. Okay, so now TC is equal to ND by CLF, which is 1.76 into 0.1, 3 into 10 to the power 8 into 0.053, 1.1 into 10 to the minus 8 second is 11 nanosecond. Now we have a related problem here, that is, I'll write as 6, example 6. So what would be the maximum Q switched power output from the leverator? Given in the previous problem. If the mode pi is the diameter 2 mm with in the rod, assume that the laser gain is 100 times the threshold value. Okay, so this is related to the previous problem. Here we have calculated the TC, so here we have to calculate the maximum Q switched power output from the UV laser, where the beam mode occupies a diameter of 2 mm in the rod. Assume that the laser gain is 100 times the threshold value. So we'll start from our equation sigma L equal to half ln 1 by r1 r2 delta n equal to 1 by sigma L half ln 1 by r1 r2. Now n naught is equal to 100 times delta n v, 100 into delta n pi d square by 4 L. So this will become 100 pi d square by 8 1 by sigma L ln 1 by r1 r2. 100 equal to pi 2 into 10 to the minus 3 square 8. So 100 into pi into 2 into 10 to the minus 3 whole square by 8, then 2.5 into 10 to the minus 24 ln 0.999.9. So this will give 6.68 into 10 to the minus 18. Now we can calculate the Pmax, that is m naught h nu by 2 Tc is given by 6.68 into 10 to the 18 into 6.63 into 10 to the minus 34 by 3 into 10 to the 8 by 694.3 into 10 to the minus 9 divided by 2 into 1.1 into 10 to the minus 8. 1.1 into 10 to the minus 8. It will give 8.7 into 10 to the minus 7. So this is the maximum Q switched power that we can have from the Q switched output power from the UV laser with the given configuration. Now I will go to another problem. This is for not for the Q switching but for the mode locking. So here the problem is, so the statement of the problem is little big. So compute the mode lock pulse width delta TP and the separation between pulses delta T shape for the following mode locked laser. Okay, so the first one is helium neon laser operating at 632.8 nanometer with a mirror cavity spacing of 0.5 meter, and the second one is a RH6G. So RH6G is rhodium 6G dye laser operating over its entire gain bandwidth 570 to 640 nanometer with the cavity mirror separated by 2 meter. The index of refraction of diffraction of a laser dye in a typical solvent is approximately 1.4. So now I will start with the first problem, that is delta T shape equal to 2 eta d by c. So now for a helium neon laser, eta is closely equal to 1. Therefore d equal to 0.5, so 0.5 meters, so we can have T shape equal to 2 into 1 into 0.5 by 3 into 10 to the power 8 meter per second. So that is 3.33 into 10 to the minus 9 second. Now the delta TP. So delta T shape is basically the interval between the pulses, and the delta TP is basically the pulse width. So delta TP is 1 by delta mu FWHM. This is the gain bandwidth for model of pulse. For helium neon laser, we assume that the mode field lays over the FWHM emission bandwidth of 632.8 nanometer times n of 1.5 into 10 to the 9 hertz. So this is a general information about the helium neon laser into 9 hertz. So that will make this 6.67 into 10 to the minus 10 second. This helium neon laser will thus produce pulses of 667. So this is 667 picosecond. So basically the interval between the pulse is around 3.33 nanosecond, and the pulse duration is 6.67 667 picosecond. Again, for the second part, the delta T shape, that is the interval between the pulses, is 2 eta d by c, that is 2 into 1.4 into 2 by 3 into 10 to the power 8, which is 1.87 into 10 to the power minus 8 second, which is 18.7 nanosecond, and the bandwidth is 6. So the bandwidth is 570 to 640 nanometer. So 640 minus 570, it is 70 nanometer. So delta nu for this particular bandwidth is c by lambda squared delta lambda equal to 3 into 10 to the power 8 centimeter per second, 6.05 into 10 to the minus 7 meter square, 17 to the minus 9 meter is 5.7 into 13 second in hertz. Now let's assume that the average wavelength of the emission occurred at 605 nanometer. The bandwidth limited pulse width would be delta tp by 1 by k bandwidth. This 1 by 5.7 into 10 to the power 13 second in hertz is 1.75 into 10 to the power minus 14 second, which is 17.5 femtosecond. So in this case we have 17.5 femtosecond laser pulse with the pulse interval of 18.7 nanosecond. So here in the mode locking we can also have the same procedure like the Q switching. In Q switching we have the electro-optic shutter, acousto-optic shutter, saturable observer. The same thing we can have in the mode locking. So I will not go into details about this because these are little complicated than the Q switching, but I can write down the techniques. So the techniques for producing mode locking. So active shutters, acousto-optic switches. So here we will have the acousto-optic modulator. So we will have a quartz crystal with a piezoelectric transducer, and then the shutter will open and we will have a pulse, and then when the shutter is closed we will not have a pulse. Yes, we don't need the details of these things, so I will not discuss. Synchronously pumped mode locking. So this is the two active methods, and then we have the passive shutters. So in synchronous pumped mode locking, that is, we have the pump laser itself a pulse laser, and it will continuously pump the gain, and then after a certain point we will have the mode lock pulse. So now the passive shutter. So passive shutters are colliding. One is colliding pulse mode locking, CPM, additive pulse mode locking, APM, and then card lens mode locking, KL. So in the colliding pulse mode locking, what happens that here we will have an interaction of two counter propagating pulses in a thin saturable observer installed within a ring laser cavity. Okay, so basically here two counter propagating pulses will collide with each other and have that mode locking. And then there is the additive pulse mode locking. So here we use a uh, optical fiber and the mirror is located at the end of the fiber to return the beam to the cavity. Then the portion of the laser pulse that travels to the fiber is reinjected into the cavity. And this way, this is a additive pulse mode locking, and then there is a card lens mode locking, which is basically based on the self-focusing phenomena of card lens. So we don't need the details of this mode locking. It's just I mentioned this because it's necessary to know. Now we'll do another example of the mode locking. So so what would be the minimum pulse duration of a mode lock Alexandrite laser? If the separation between mirrors is 2 meter and the rod is 0.1 meter long. What would be the separation between mode lock pulses? So in this problem the given data is Okay, I'll just read the problem again. So what would be the minimum pulse duration of a mode locked Alexandrite laser, and if the separation between mirrors is 2 meter and the rod length is 0.1 meter, then what would be the separation between mode lock pulses? So basically we need to calculate delta T shape and delta TP. Okay, so now D equal to 2 meter, L equal to 0.1 meter, and refractive index. This information I write in between the problems are like given in the problem, so I just don't mention at the start of the problem, but it is given. So refractive index eta L is 1.74 for Alexandrite. Now delta mu FWHM is 2.6 into 10 to the 13 hertz. So this information and this information are given basically, and eta L is here. Sorry, not eta L. Oh, sorry, 1. Now delta TP is 1 by delta nu FWHM, which will be 1 by 2.6 into 10 to the power 13 hertz. 3.85 into 10 to the minus 14 second, which is basically a 38.5 femtosecond pulse, and delta T shape is 1 by delta nu, which is 2 eta C D minus L plus eta LL by C, which will be 1 D minus L plus eta LL by C. Then I'll just put all the values. D is basically 2 meter, then L is 0.1 meter plus eta L is 1.74, and then we have 0.1. So this becomes 3 into 10 to the power 8, 1.38 into 10 to the minus 8 second, it is 13.8 nanosecond. So here we have the separation between the pulses as 13.8 nanosecond, and the pulse width is 38.5 femtosecond. So basically the pulses are coming like this. Sorry, this is very bad pulses. So this is 13.8 nanosecond, and this is 38.5 femtosecond. So but in a pulse laser we don't only have a simple mode locking or gain medium or something like that. There we have some, in that case, for example, in titanium sapphire laser we have sapphire laser, then we have a stretcher then we have regenerative amplifier. Then after that we have some part of amplifiers. Then we have a compressor. So all these things we have in a pulse laser. So first the laser is generated in a certain condition, then it is stretched. So basically we have a laser pulse like this, and then after the stretching it will be like this board, and then it will be amplified like this, and after that this will be compressed. So basically all the whole pulse is compressed. So then we will have a very sharp peak. So basically we will have a small pulse to a very large pulse. So this thing is known as the CPA, sharp pulse amplifiers, which is generally used in recent days laser to generate the high intense pulse from the pulse laser. Okay, so today I will end here, and we'll meet on the next Friday again, and we'll discuss some more concept and more problems. So I will end today's session.
Sir, please could you repeat the last point where you just mentioned where CPA is used?
Oh, CPA is used, basically this is chirp pulse amplification. Okay, so by chirp I mean if you uh, the beam has very different, is a mixture of wavelength. Okay, we only talk about the central wavelength. So when we mix chirp with the pulse, then okay, so let me draw it. This is a pulse. When we mix chirp with it, this will become uh, this thing become broadened. So this pulse is broadened, and this is basically chirp pulse. Okay, this is the normal pulse that is generated in a laser. Then we amplified the whole pulse, and then this thing becomes like it has like this. So this thing become like this. It is amplified, and then finally in the final step, like in the compressor, we compress this pulse. So basically, for example, if this is some 50 femtosecond, this will be something around 1 picosecond, then it is amplified, then it will also be 1 picosecond, and then it is compressed to again 50 femtosecond, and this will be like this very sharp peak. So if this is some around some uh, milliwatt pulse, then it will be of some gigawatt, I mean the peak power, and the duration will be almost 50 to 60 femtosecond. It's not possible to get back to the 50 femtosecond, but it will be around 60 femtosecond. So this is known as the CPA process, chirp pulse amplification. This kind of process is used in the recent days pulse laser.
Okay, sir. Thank you, sir.
Welcome. So okay, so I'll end today's session, and we'll meet on the next
Yes, sir. Thank you, sir.